was about to get to the point where I told Lucas he can't do what he wants to do. So that's
my favorite part.
That was that highlight of my day. I'll get there. Sorry, I was about to get the part where I can tell you you can't do what you want to do. But anyway, okay. So this is the power flow. Net megawatt this is what would actually be in the power flow. So let me just go play with a little case to show you what this would look like. So if I had a load here and I came in and I added, say, 43 megawatts and 7 megabars at this load, and I hit OK, what you'll see on the diagram is this load just dropped. It used to be 125 megawatts. The value that's shown on the diagram by default is the net megawatt. And we also draw a little sun symbol there. Kind of let you know, hey, there's some distributed gen here. So if I were to look.
So does it assume all of there is solar?
Yeah, right now.
Okay.
We don't have a way for you to customize that symbol right now.
Who draws those for you guys?
Me.
Nice.
Just great. It's like the skill. So if you look at the load then, that was the bus, not the load. So inside the power flow, we're all just using the net megawatt all the time. So as far as power flow goes, this is just accounting, just keeping track of megawatts and assigning it to one or the other. When you get to transient stability, though, it's trickier. And the reason is because of the distribution equivalent. So in power world, with a particular load, you can assign a distribution equivalent model to it, and a load characteristic, and a load distributed gen model. So kind of playing in the GUI here. This isn't really in your slides. I just went off book here.
Jamie unplugged.
Yeah. So in here, there's a thing we call a load distribution equivalent type. So usually you're just going to get this from the DYD file, but I might create this. I'll call it my DPA feeder. And if you look at it, you're just putting in all the input parameters of a particular feature. Then when I'm over on a load, I can say, just like when I was in a generator dialog where I had a machine, an exciter, a governor, a stabilizer, and other, in the load you have a load characteristic, a load relay, a distributed gen model, and actually up here is the distribution equivalent. So I can say this load belongs to this distribution equivalent. And then I might come down here and say its distributed gen model, we only have two. There's two models right now. There's a DG-PV and a DG-DERA. These are the only two distributed gen models right now.
One of them solar. What's the other one?
They're
just different flavors of solar?
The DG-DER is like a simplified agglomeration of an REGCA, an REEC, and an REPCA. So if you come in here and hit, I think it's you might not have this in here. Yeah, actually it just says, go look at the DERA documentation for a generator. So then if I go here, it's this. And essentially, yeah, it's kind of complicated, but it's better than having three models. So I get it. If you look, it's got some familiar things. PI controller, frequency input, voltage input, over here, current. We're going to talk about renewable models later.
We'll send that to Grace Hart.
But the point is, you just assign for this load, this is how the distributed gen behaves, and for this load, this is how the load characteristic behaves. So they're all chopped up into separate models. So the CMPLDW, I mean, the reason it has 130 some parameters is because it's really like 6, 7 models in one. It's like it's got a feeder, it's got 4 induction or 4 motors, it's got an electronic, a static, and then the distributed gen now as well.
I'm pretty impressed you can solve all of that different stuff.
Yeah,
That's what I'm trying to.
no, exactly. Yeah, and it got slower. You know, when WEC, part of the growing pains of switching to the composite load model is all the simulations got slower. Because why? Well, because you're modeling a lot more. You took all your zip loads that were just a function of voltage and turned them into four motors and a feeder. Okay. All right. Yeah. So what I wanted to talk. Shall I just draw it up here? So when we initialize this model, if we start with 140 megawatts of load and 30 megawatts of DER, then we've got a net of 110. So we're going to calculate, because this has an R and an X and impedances. Inside simulator, we're going to calculate how much power makes it all the way down here to the end of that feeder. That's part of our initialization. We will calculate that. There's usually, 5% loss or so. That's how these feeders are set up. You get down here, and by definition, because I decided it would be that way, we assume that all the distributed gen just translates directly down there and does not contribute to the losses. Basically because it's easier to code. And all of the losses are assigned to the loads. So we get 103, so we started with 140 megawatts of load. We're down at the end of the feeder, we have 133. And then those get split up amongst all of these pieces. I'll comment when you're looking at reporting. If I do a plot of what is the load megawatt at a particular load in transient stability, I get this number. So it's essentially including the feeder losses. Because what you're asking, at least I assume, you're asking what is the transmission system seeing as the load. Otherwise, the moment you switch to the composite load model, the load in your system drops 5% because the losses just went up, and you really want the reporting. So that's it. I bring it up because that's what PowerWorld and GE did, but I know PTI didn't do that because people are like, why is your load off by 5%? I'm like, it's not. PTI's is. But PTI always gives me the right answer. So, not this time. So they're reporting this number. But the answer is they're the same. It's just what do you consider load? And from PowerWorld's perspective, the load's up here.
That's actually the correct perspective.
I think so.
Well, I think because that's how the power flow is set up. I mean,
that's the load, exactly.
Yeah,
this
you
is
have
just
your
part
little,
of the dynamic model.
Yeah, you have your arrow on that feeder bus.
Yes. Correct.
Yeah.
Yes.
Jamie,
Mm-hmm.
is it possible to output this feeder, this composite load feeder network, like you do your change of stability initialization? You're doing all this calculation. Can you output like an aux file of all the subnet of all those feeder subnetworks?
What you can, even more than that, you can come in here. Where's it at? You go. There it is. No, that's not it. I need to call Caroline right now. There's a spot where you can tell it to expand. Okay, maybe it's under loads. Okay, it's here. Yeah, I think I have to be in edit mode. But you could go into a web case. No, let me just do a web case.
the load record, then create composite load
Yeah.
model.
Yeah, and it actually will change your power flow model. I mean, you don't usually want to do this.
Oh man.
Not bad. Let's get the diagram.
Now we really have to call Caroline.
Yeah, now you just have to restart it.
Oh, there we go. There's something with the diagram.
How'd you get the problem to stop?
I just hit escape over and over till it went away. It was something.
No,
Yeah, I think you just have to restart your.
That's usually what.
don't restart. You have to restart Power World
Just
if it
kill
starts
that.
doing that.
Run
Yeah,
the
that's
kill
what
that
I just
thing
did. Something with the diagram, I'm sure.
I have problems with that.
Yeah, people always ask us, what's that address mean? The address means we screwed up. It doesn't tell us it.
We or me?
We meaning Power World.
All right.
It could be me. It's funny, we have a code management system in the software, and one of the features of it is you can right-click on a file, and there's a drop-down that says blame. That's what it's called.
Oh,
And
that's
it pops up the source code for that file, and on every line of code, it tells you the last person who edited that line of code.
It's the list of shame.
It's the list of shame. It's like, who added this?
So is that announced at Christmas parties or something?
No,
like for the year?
the problem is when you pull it up and you're like, who did this? And then it's you.
Then you get real quiet.
Yeah, then you don't tell anybody. Oh yeah, it was me.
I got something to do today.
All right, so when you're in here in edit mode on a particular load, there's a right-click option that says Create Composite Load Model. It's actually not a great caption. It should be expanded. So if I look at this load, it's got us. I need a load that has CMP. So here's a load. If I right-click on it and I look at the bus view right now, it's just got a load right there.
10.609 megawatts.
If I right-click on it and I go here and I say Create Composite Load Model, it pops up something. It says Do not add transformer reactance if it's 0. Yeah, just leave those options. And if I hit Create, that load just disappeared. But if I go back into my bus view and where I was at, what you see is apparently this one didn't have a transformer because it didn't put one in. But it added a bus and created all the components.
Well, there's,
Oh, is that
there's
because-
an option that's auto check that says don't create.
Well, it didn't create it because there was a, because it, correct, it didn't create it. Oh no, this is the wrong bus. It didn't create it because this bus was below a magic threshold that said never create a transformer.
Oh, what's the magic threshold? Is that like?
It's a user option.
Mm.
So it's under options, load modeling. No, that must have just been 0. Yeah, but it's 0. So that means that that particular feeder must have just had an X of 0 on it. So if I pick one that doesn't, here's the X. So let me pick one that's DSW _ C.
So are each of those zip models, or are those?
Well, in the power flow, they're just zip models. But we have created, if I can look at motor A, we created it's got the motor _ CMP,
Mm-hmm.
which has all the parameters for that particular kind of a motor. And if I look at motor D, It'll be the LD1 pack underscore sim. Or actually, I guess just LD1 pack. Here. And then the P, this is the power electronic load, which is the LD. That's not right. I should have put it in LD black. That needs to be fixed. And then this will be a zip model, basically.
That's the static.
Yeah, that's the static. Yeah. So it's just splitting it up into pieces. And it permanently changed the power flow. So normally when you run transient, it doesn't do that. It like makes a copy, messes with that, and then when you're done running that stability run, it throws it away. And you start over and make a new one.
Now with those, it still has constant power parameters?
Correct. Yeah, so
Okay.
you can use this in the power flow environment.
With the constant power assumption?
Yes.
Okay.
Yeah. Go ahead, Eric.
Scan the whole case
If you were to select all the loads
and then right-click the
and then right-click, it would do all of them.
There was a paper in 2012 where you can convert those to zip models to get a more accurate steady state
Okay.
assumption.
Yeah, we haven't implemented that because we're just
Okay.
putting
There
them.
was a 2015 paper presented at ESPS that somebody wrote that did a really good job showing how to do that.
Okay.
So
That was- That was 2012.
2012. Oh, wow.
We're getting older.
You're getting old.
You've crossed where you used to be the youngest person in the room, and now you're in the upper half.
The right James wrote the paper. It's pretty good.
Oh, I didn't catch.
He wrote
Thank
the
you,
paper.
James.
He took the composite load models and ran transients and then curved all of the zip models to the different
Okay.
components.
So you knew that feature was there.
No, I bet
didn't?
Gordon pestered you because he always wanted to
correct, he
use
did.
my paper in the
Okay.
power flow world. So,
Okay.
probably 70% of it's now implemented, but the last 30, instead of using constant power, if you actually use the zip equivalent models in the
Yeah,
paper,
it could be. Yeah.
then, it's accurate down to about 0.7 per unit, but then, assuming you believe your composite load model and the percentages there, you have a more accurate power flow steady state simulation.
Yeah, and your power flow steady state isn't accurate below 0.7.
Right, exactly, so it's great. Yeah.
So, all right, a comment about initializing these models. And then I think I'm going to be done. This is kind of a software vendor secret. When we code a model, the hardest technical part is figuring out how to initialize it. Coding the numerical integration that I'll go through this afternoon, it's hard, but you figure it out once, and it's true for all models. And you figure it out over the course of a decade. This is what happens. But initializing models is hard. Actually, John Undrell told me once, what you should really do is give your software away for free, but charge people for initializing the models. Because that's really where the work is on the software vendor side. But I was like, I don't think that would be confusing, John. But initializing the models, you have to figure out where they start. So for instance, one of the issues on something like LD1 pack, the air conditioner model, is the input data gives us this red curve and this green curve. And it's not really clear, but we have to calculate where that curve meets. And you have to literally we have to run Newton's method and iterate to figure out exactly where that curve meets and keep track of it. So that's something that's in the initialization. So
Does it change once initialized? Or
no. It will be different for every single load.
But it's a one-time thing?
It's a one-time. It's part of initialization. Yeah. Another thing is on an induction motor. If you go back to an induction motor, we drew that picture of a circuit, right? And we said it was this. And we said this is the steady state behavior. Well, if you think about it, that means that if I know what power is here and voltage, then the reactive power is going to be a function of whatever the initial power is. So when you give us an induction motor, you give us a load
that says it's got a P initial and a Q initial. And you tell us it is an induction motor with these parameters. We're going to calculate the initial power kind of transfers right to the induction motor, but the Q of the motor we have to calculate. And there is never a motor that you give us where the Q for the motor matches what you actually gave us in the power flow. They're always off. So what do we do with this like extra Q? And the answer is engineers in the 1970s said, we'll just put an impedance in there. So every induction motor in its model has an extra shunt just hanging out there. Okay, so one of the things that can be kind of weird with the composite load model is we've got this motor here. Maybe it starts out as 100 megawatts and 50 megabars. And we do the math and we figure out, okay, that's really 100 megawatts and 80 megabars. And so we stick in basically an extra, in this case it would be an inductor, or I mean a capacitor, which is 30 bars at that particular point. As we start tripping this motor, and we say we're tripping 50% of the motor. All right, if I go in the lab and I've got an induction motor running, can I trip half the motor? No. I can either trip all the motor or none of the motor. But in the software tools, we trip half or 30%. And so what we're really doing is we're just taking these values and multiplying them by a scalar, because that model is really meant to represent thousands of motors, and we're saying we're tripping half of those motors. All right, the issue is that I've seen support questions is somebody will have tripped like 90% of these motors. And so essentially this model's down to like 10 megawatts and 8 megabars. But when I look at the net showing up in the transmission system, you get this weird thing where the motor's supplying a whole bunch of VARs. And it's a reasonable thing to ask us, what the hell is going on? I thought I tripped it. It used to be consuming 80 VARs. Now it's providing 22 net VARs because that shunt is just hanging out. And that's just how the model works. That's an artifact of the numerical stuff. Because when we initialize the motor, we put in this fake impedance to just kind of get it to match, and then it just sits there. The only time that goes away is when you trip the entire load. So, yeah.
So, but isn't there any scaling or anything?
Not on that. I've debated, it's like, it would take like 4.5 years for the software vendors to agree on what to do with that, so I've hesitated to bring it up. But in a way, it's like we should probably scale that also, but none of us do.
So what is that? But if we're getting a bunch of extra bars, then...
Well, I mean, it's ultimately showing up because your initial power didn't really match an induction motor.
Right, Jim, but I guess what I'm worried about, not in that initialization step, but if we're in the dynamics, the things are being tripped.
Correct.
Partially being, there's only partial trip. That's still sitting there unscaled.
Correct.
And especially in some issues like we have where you've got maybe voltage stability, voltage related stuff that you're worried about. That looks like I'm getting extra.
Well, it can be
bars.
either direction too.
Okay.
You know, it could be providing bars or it could be sucking bars.
Either way,
it just
that
depends.
sounds like I've got another bar something there that's not really there, at least that magnitude.
Correct.
That, and if that's across a huge swath of the system, that sounds like a big error.
It could be. It is washed out a little bit with the composite load model because we like accumulate all this air across all these individual components. And so, you know, this one might be plus 30, this one might be minus 10, plus 15. You know, we sum all that up,
and then stick it here at the end. Actually, it's more complicated because we assign it to this feeder. But yeah, I don't know how much I want to go dig into that.
Where do you see where I'm coming from?
No, I understand what you're saying, and that's why I bring it up,
Okay, right.
because it's kind of a hidden secret in this composite load model.
When you create the composite load model, what's its ID? Is it just EX for extra or something, or?
It's running over. You don't interact with it. It's only in the transmission, or only in the transient stability simulation.
I mean, when you're converting it, like that step.
Oh, that step. I give
Yeah,
it
yeah.
different IDs.
Kind of like the slop load.
Oh, that part. I think in this, I think I spread it out across all of them. Or you know what? I think I stick it in the static.
Or just stick it in the static, yeah.
Which is, it's actually not the same thing that happens in there.
But mathematically it's equivalent because it's just being treated as a.
Actually, no, sorry. It shows up here. It shows up as a line shunt on the feeder.
Okay.
That's where it's at.
So it's a little hidden even from that view.
Yeah. Yeah, I mean, I call them extra bars. It's like just to get it to match.
And it's a shunt, so it's a constant
an
impedance.
It's
Okay.
an impedance. And it can be positive or negative.
Mm-hmm.
And, you know, it gets, when a composite load model, it at least gets summed up across all of them, so some of it cancels out. But it can be, it's in there somewhere. You know, in the composite load model, it'd be really hard because there's like one impedance across all these components. So when you say that motor A tripped half of it, I don't really know. I don't know who to assign this impedance to. It's like who does it belong to? So I think, John, I think of the worries with load modeling, this should be low on your list, to be honest with you. But it is something we may have to look at someday as an industry.
Well, and you're saying that, Jamie, because it's your belief that it balances across the.
It literally just depends. I mean, if you have an initial input value where you've got like 100 megawatts of load and 400 bars, you're going to get a huge shunt down here because they're not that input data is weird. So then you'll get a big difference, but at the same time, your input data is weird. So as long as the power flow megawatt megabars kind of match what these things are doing, it won't be that bad. But when you've got 8,000 loads, I'm sure I can find 5 of them that are weird. You know, it's like there's always something. Okay. All right. The last. Yeah, this just kind of walks through how it actually initializes the model. I'm not going to go through that. Mostly, I put this together. Honestly, I put this together in about 2015 or so because when GE implemented this model, they never really documented what they were doing. So it took me probably about 3 years going around and around figuring out exactly what to do. And then PTI showed up, and it was kind of a disaster when they first implemented this. And I was a little bit sympathetic because I was like, I know exactly what they're going through. It's because it's not really clear how to initialize this thing. And there's a lot of kind of arbitrary choices. And in particular, this feeder impedance right here, we give it as like 0.03 plus 0.03 or 4, somewhere in there. But that's the MVA base of this thing is based on the megawatts up here. So the bigger the assumption in this model is that the bigger the load is, the beefier the feeders are going to make sense. The problem was that this load might be 140 megawatts, and if it's 40 bars, megabars, that's fine. Basing it on 140 MVA base is okay. But there were some loads where the megabars would be like 8. Doesn't sound bad.
and the load would be 0.1 megawatts. If you pull up usually not a wet case, but you put in your own data, people get loads like this suddenly in a case. Clearly they're silly, but they happen. And then we're basing this feeder impedance on this MVA base, and then trying to push 8 VARs across it, and just collapses the network. So the simulator has all kinds of tricks in it to look at your crappy data and detect it, and basically ignore the feeder and just zero it out. But it was honestly, when they made this distribution equivalent, they should have made it based on the MVA of the load, not the megawatt. But the train left the station. It's been 10 years, so nobody wants to go back and change it. So what happened in the software tools is what happened initially in the software tools is you guys get your data from WEC. So WEC staff just would go in and clean all this up because they'd run it, PSLF would crash, and then go in and say, okay, well, this load doesn't belong to the distribution equivalent anymore. And they'd just get rid of all the errors for you. But of course, as soon as you start messing with your case, then you would run into the problems. They were just hiding it from you. So eventually we put in some options under transient stability under option load modeling that basically say, do not use, in Power World we implement it as any load that we consider complex, meaning it's meant to represent an aggregate of stuff. So CMPLDW, motor W, we have a comp load and a clod model. All of these, if the load is less than some megawatt threshold, we'll never use a complicated load model, because what's the point? Or if the PQ ratio is less than 0.24, again, you can edit this, so that in that case it captures this, as the PQ ratio here is 0.025 or something like that. 125. Whatever, it's very small. So we can throw that out. Or if the initial per unit voltage is low. And then similarly, we have this option that says if the load bus nominal KV is below a threshold, we'll never include that step-down transformer. So what was happening is people would have in the power flow case, they'd have a 115 kV bus here. In the power flow, they might have a step down to 13.8 kV, and then they would have their load. And they had put that in the power flow. And then they assign this load to a distribution equivalent that also has a step down transformer. So then when we put it in the composite load model, we do this and put our loads down here, but this is silly. Those aren't there. The point is, in the power flow, somebody already put the step-down transformer. So this says that any load that has a nominal KV below, usually I set this to 40, then just ignore that transformer in the input data.
When you do put in a step-down transformer, what's the default low-side voltage? 12 and a half, or?
It doesn't matter.
Oh, okay, it's just whatever.
I don't know what we put. I think we might just put 1, because nobody's gonna. It's just an equivalent down there. Everything's in per unit. So I don't know, but it just doesn't matter. It's not like you're ever gonna. You can report the voltage there, but you have to do it on the load record itself. So which one of these guys has it?
looking at the load at bus 5. So when you're doing plots, you get all these sort of general fields that you can do on all loads, and then there's folders down here. So you can look at like a load state. Actually, I don't have a load there, but if I look at the distribution equivalent, you'll see that if I wanted to know what's the voltage down at the load bus, that's here. What's the low side bus? We call this the low side bus and this the load bus. But the point is, there's not even a way to ask what the KV is there, because it doesn't matter. Okay? Go ahead, Eric.
Does it matter though? I mean, is it equal BI, so if you went like really low, don't you get a lot more I? I mean, I guess
it's all in per unit at this point.
Oh.
The impedances are normalized to per unit on this MVA base. Yeah. So it ends up not mattering.
Okay. So you still might have a nominal I, or like a regular, yeah, I see what you mean.
Yeah, so I mean, I don't think we even let you know what the current is down here. I don't think that's in here. No, so we can tell you megawatt and megavar, but if you were to ask current down here, then you'd have to tell us what is the nominal voltage, and your answer would be, I don't know.
What do you assume in your when you convert it?
Huh?
What's the assumption when you convert it and you look at the load bus
I'm
there?
not sure. We have to pick something.
Right. So 12 and a half.
We did 12 and a half, but that's what it was here. So I'd have to go look at what the transformer is. When
When you add one.
yeah. And the answer is, when you're done, if you don't like what we picked, you just go change it. You can just change the nominal KV of a bus, and it doesn't affect anything. Your currents will all change, but internally we're calculating everything in per unit, so it doesn't matter. All right. So I just introduced the concept that there's a really large amount of data that can be put into a power system case, and Richard's going to talk about how bad it can be.
I'll just use mine if I can present, and then we'll get Lucas in there too. So we'll just finish up before lunch talking about, I want to retitle it. It's not bad data. It's just actually the data we have in the wet case.
That's a good point.
It could be agnostic. Some of it worse. Some of it's so curious you can't really define it enough to actually call it bad. It is just what it is. But Lucas, do you have what I thought just sitting there though was it might be instructive to go first and talk about what it is for those of you who don't know what goes on at SDWG or SRWG. It can be informative to know of the work that goes into making wet cases when they're published pseudo as best we can as far as data goes. So I was going to have Lucas chat a bit about specifically transient stability and what checks are done in wet cases, if that makes sense.
What was SRW? Instead of conferences?
Used to be so you meet in Salt Lake a couple times a year, system review worker, now system data. That's where the cases get built. Most of what we do is that's where the 11, 12 cases that WEC spits out get finalized. And they'll send, we had an area coordinator at Columbia Grid. Now I'm guessing it's going to be Northern Grid that's going to kind of mediate that. But here's your database from the last time we did a light winter. At my time at Avista, what's changed? Give us the aux file to fix that, send it back. What's changed both in power flow and stability? And then it just gets mixed up some.